Hi, everyone. I'm going to talk about new generalization bounds for uniformly stable algorithms, and it's a joint work with my wonderful colleague, Jan Wondrak. So we're going to talk about generalization bounds for learning algorithms. And for this purpose, let me define some, this doesn't work. Let me define the following general setting. We'll have a learning algorithm, which gets as an input a data set S, which consists of n points drawn ID from some distribution P, and output some model, which depends on the data set, which we'll denote by WS. And we'll also have a loss function, which for any model W and point Z in the domain will give the value of the loss. And the main quantity of interest is this estimation error, also referred to as generalization gap. That is just the difference between the true expected loss of the model output on the data set S and the empirical loss. And we'll denote this estimation error by delta of S. So we're interested in generalization bounds, which are based on stability. Stability is this old and fundamental approach to generalization, which roughly states that algorithms which are not too sensitive to individual points will produce models that generalize well. We'll be interested in specific and relatively strong, or maybe very strong notion of stability, referred to as uniform stability, which is defined as follows. An algorithm A has uniform stability with parameter gamma with respect to loss L if for any pairs, two data sets that differ in a single element, the loss of the model output on the first data set and the loss of the model output on the second data set evaluated at an arbitrary point in the domain will differ by at most gamma. You can think of it as the loss on every point in the domain having the standard bounded differences property with parameter gamma. So for scaling purposes, we'll think of loss as being in the range 0, 1. So stability is also in this range. And the most interesting value of parameter gamma for our purposes will be roughly 1 over square root of n, since that's the rate at which most learning algorithms generalize. So there are a lot of results about generalization properties of stability. And let me very briefly recap the ones which are most relevant to this work. So already from the early works, you can extract the following two bounds, that the expectation of the estimation error is at most gamma, and that the square root of the second moment of the estimation error is at most square root of gamma plus 1 over square root of n. So the first bound does not tell us anything about the typical values of estimation error, because this value can also be negative. We define it without the absolute value. And the second bound has already worse dependence on the stability parameter, plus this 1 over square root of n, which is basically the sampling error and is unavoidable. So the first high probability bound, based on stability, were given by Bousquet and Delizeev, who showed that the probability that the estimation error exceeds this bound of gamma times square root of n log 1 over delta plus the sampling error is at most delta. So which is great. It holds with high probability. Dependence on delta is logarithmic. But it has additional factor n, which makes this bound vacuous in the regime we're interested in. So another relevant result is that of Shalev, Schwartz, and others, who shows that if your algorithm happens to be the RM, the empirical risk minimizer, then the first moment of the estimation error is at most gamma plus 1 over square root of n. And this is can be easily seen to be optimal. So this has been the state of the art for a while, until about a year or so ago. I started working on this problem with Jan. And last year, we published a work in which we improved two results. The first one is that we improve is this bound on the second moment, where we give the tight bound of gamma plus 1 over square root of n. And the second one we improve is the high probability generalization bound. We improve from gamma times square root of n to square root of gamma. This is no longer vacuous, but still it only gives the tight rates in the regime where gamma is very small, on the order of 1 over n, which is not the interesting regime. So this brings me to the result in this work, and that's the main result. We showed that the probability that estimation error exceeds gamma with some logarithmic factors plus the sampling error is at most delta. It's easy to see that its result is optimal up to these log factors. And if there are any log shaving guys here, you're welcome to take a stab at it. And also another way to think about is that it gives the same concentration. Another way to think about this result is that as long as the stability parameter is at most 1 over square root of n, the estimation error is on the order of the sampling error. So this essentially solves the question of what are the generalization properties of uniform stability. But you might still wonder, why should we care about this bound? Of course, my personal answer is that it's sort of hard to imagine a more fundamental question about generalization and concentration of random variables that has not been solved in a while. But that's a matter of personal taste. In addition, but there are also some very interesting applications, and let me briefly mention those. So the applications are in the context of convex learning problems, and those can be reduced to stochastic convex optimization. So it's important to understand what are the generalization properties, generalization guarantees that one can prove for stochastic convex optimization algorithms. And to make this discussion more concrete, let's look at a specific and standard setting in which the our set of model is the unit ball in d dimensions. And our loss functions are convex one Lipschitz functions over this unit ball. And the goal is as usual, is to minimize this expected loss. So there are several approaches to understanding improving generalization bounds in this context. So the first one, and the most standard one, is based on using an online algorithm with a regret bound and then an online to batch guarantee. And applied to this setting, it would give us a bound on excess loss of roughly 1 over square root of n, which even holds with high probability. And it's all great. The only issue is that this type of approach can only be applied to algorithms which make a single pass over the data, which is not the kind of algorithms which are usually used in practice. The other approach one could use is the standard approach based on uniform convergence. And this would work if you are using kind of a simple linear model. But in general, for the general problem, we now know that this cannot give a better bound than square root of d over n, which in the setting which in high dimensions will not give anything interesting. Finally, there is an approach based on uniform stability. And there are two ways to get bounds from this approach. The first one is by using regularized ERM. And the second one is based on gradient descent methods with a little bit of smoothness. And for both of those approaches, if you balance the empirical excess loss and the stability, you will get this stability parameter of 1 over square root of n. And as a result, for both of these algorithms, it has been known that the algorithms generalize in expectation and has been open whether they generalize it with high probability. So just by plugging our bound, we'll immediately get high probability bounds for these algorithms with nearly optimal 1 over square root of n. So I don't have much time to talk about the proof approach, but maybe I should just mention that sort of the reason why it took a while to get here to this point is that standard approaches don't work. So we have to basically come up with a new approach for proving concentration. And if you're interested in this topic, you should definitely take a look. I think you'll find it interesting. And at a high level, it's based on kind of reducing the bound to itself via various reductions. Let me conclude with kind of a couple of high-level notes on the role of stability and generalization in machine learning. So one sort of strong point of stability is that it allows us to analyze algorithms which we cannot analyze using the standard techniques like uniform convergence and on-light to batch. But it also has limitations. One of it is that we have a relatively limited set of techniques to prove generalization bounds. And they seem to require new tools and ideas. I think one of these tools was given in this work, but more work is needed. And the other limitation is that we have a relatively limited set of algorithmic techniques which have stability. And here, one promising direction is connections to differential privacy. Specifically, for example, in a very recent work with Yuval Dagan, we showed that using this connection, one can give uniformly stable algorithms for all DC classes with nearly optimal rate, which apparently wasn't known. Anyway, that's it. Please let me know if you have any questions.
We have questions? Now let's end this.